We've seen that we can use the assignment operator with pointers. We can do comparison as well, but what about addition and subtraction? So using the addition and subtraction operators and using pointer identifiers as operands to those, what's going to happen when we do that? So that's basically what the next section is going to be about. So we can apply a temporary offset to a pointer in memory, including to an array name, since this is going to return a constant pointer. The amount of offset is determined by the type that the pointer points to. This is once again similar to using an index in the subscript operator. So the amount of offset is determined in those cases by the type. So the type of the array, if it's just an array, and the same thing when you use it with a pointer, of course. So once we have that temporary offset, we can then dereference that address that it will return from that calculation to read from that address or write to that address. So the offset is basically calculated as n times the size of whatever type it is. So in an example, we have 1, let's say we have some offset that we want to apply. Let's say we do pointer plus 1, so ptr plus 1. How much actual offset is that going to do in memory, right? Well, it's going to be 1 multiplied by the size of, let's say we have an integer, so that's going to be 4 bytes of offset. Let's say we have 2, well that's going to be 2 times 4, which will give us 8 bytes of offset. Of course, if it is a double, then the size of a double is going to return 8. So if we specify 1 as the offset, then it's going to do 1 times 8, which will give us 8 bytes of offset. So then it's basically going to jump over the current element in memory, the current double in memory, and it's going to move to the next one. That is if we're actually pointing to an array. And also finally, if we have a character and we do an offset, we specify 1 as the offset, so we do some pointer, so ptr plus 1, and that pointer is a pointer to a character, then it's going to do 1 times size of char, which is going to be 1 times 1, and then that'll give us 1 bytes of offset. From this we can see that pointer arithmetic is used primarily with pointers to arrays. If you use arithmetic with some pointer by itself, that points to some random address, which is not the start of an array, that pointer can now point to some random memory. You're not going to know exactly where it points to. And then you can read some garbage from that memory, or you can write to it and then maybe inadvertently go and corrupt that, and you'll get crashes and so forth, corrupt data. We'll take a quick look at this in an upcoming demo, but again, we primarily use pointer arithmetic with pointers to arrays. Here's a quick demo. I'll show you this later on in Visual Studio. We have an int demo array with the elements 2, 4, and 6, and then we have a pointer to an integer, which will point to demo array. And then between parentheses, we have ptr plus 1. That is going to calculate the offset, and then it's going to dereference. You can see we have the asterisk there as well. So it's going to basically calculate the memory position, right, doing that offset calculation. It's essentially going to give us a pointer which we dereference, and then we can store 700 in that location. Then we can also do this with the array name, so either with the array name or the pointer name, since the array name in this context is going to return a constant pointer as well. So we can do demo array plus 2, for example. That is going to calculate the offset and return a pointer to that address in memory, which we then dereference, and we assign 7 to that. And then we can do a similar thing when we want to do console output. You can see we do temporary offset calculations once again, followed by dereferencing, and we simply go and print out whatever we get at the memory location. So in this case, it's important to realize that these are temporary calculations. We are not modifying what the pointer is pointing at, and we are not modifying what the array name is pointing at. We simply use those names or those identifiers in offset calculations, which you can think of as returning another temporary pointer to that address, okay, that we'll get back from the calculation. We then dereference that temporary pointer that we get back, and then we can use that to assign, so to read from or write to wherever that is pointing, since once again that is what we do when we dereference, right? Okay, before we move on to the usage of the addition and subtraction operators with pointer variables, that is, I'd like to show you another example using the subscript operator, or also referred to as indexing, because this is also referred to as the index operator. And in this example, I have an integer x and an integer y. I also have a pointer to an integer, which I initialize to the address of x. Then I do the indexing basically, so I do the pointer and the subscript or index operator 0 to 2, but this is actually undefined. Subscripting or indexing is only defined with arrays. We don't have an array in this example, right? So we're doing some offset to the pointer, but it doesn't point to an array. So 0, if you think about it, the pointer is going to point currently to x, which stores 5, and this here will not do any offset because we have 0. So that should essentially return 5 to us. Okay, so this would print out 5. But here I do offset, so I do 1, which will do 4 bytes of offset from wherever this pointer points at in memory. And where can that be? Well, that can be anywhere, right? It can be to some of our other variables or some other chunk of memory. Now in this case I'm simply printing out these values, but we can of course use this indexing method or subscripting. As you are familiar with already using arrays, we can also go and add values. If you remember from the array section, we can do this sort of notation. So we can assign 3 to that first element. And what's that first element? Well, we don't have an array. In this case, it'll actually store it in x, but that's just because it is set to 0. So it doesn't add any offset in memory, right? I'll just comment this out for the first run and then we can come back and run it again just to check if it applies that change properly. But again, indexing is only defined with arrays, and that will include pointers to arrays. And undefined behavior generally leads to corrupted memory, because once again we can do this here. We can assign some value to, let's say, 1 or 2, but those are undefined because it's just going to do some offset, and then we assign 3 to that memory location. And then of course we can corrupt some data, so either some other variable in your program or some other chunk of memory, right? Okay, I'll build and run this. And this is what I mean. So it prints out 5 properly, but then we just get some garbage using index 1 and 2. Just for fun, let's do this. We try and make a change to that. Before we go and print that out, and you'll see this actually works. But imagine if you try and do a change like that to these memory locations. Again, we can corrupt that memory. So I felt like this section was important to add because we can do a different notation for the same thing. So even though I'm using subscripting or indexing here, we can do an offset in another way. And in whichever way you go and do the offset, it's important to remember again that it's really only defined with an array or with a pointer to an array. Okay, so what happens when you add some integer literal to the pointer variable? Here you can see ptr1, and then I do +1, so that is a literal of 1. And I place this between brackets just to make it easier to read. And then also later on we'll be dereferencing it, so for the most part we'll be using it like this in anyway between brackets. So I just added those brackets, and here I'm getting the address of demo array, so the address where the second element in that array is located. I'll just build and run that so we can see what happens, and you'll notice that we get the same address out to the console, so both of those give us the same address. Okay, now you might ask, can we do the same thing with the name of the array? So here I'm just using the array name directly, and I do +1, and here I do the pointer, so pointer +1. Let's see what we get now. Again, all of those will now print out the same memory address. This is actually going to be the second element in that array. So basically what's happening here is we do an offset. So just like the index within that subscript operator is essentially an offset from where that array starts in memory, you can also do that offset using plus and then add some integer literal. This is not going to add 1 byte, okay, because a pointer, for example, is once again just an address. So +1 you might think will add 1, maybe 1 byte of offset to that address. But that's actually not what is going to happen. The amount of offset that it'll add will actually depend on what the pointer is pointing at. So in this case, it is a pointer to an integer. So +1 will actually give us 1 multiplied by 4 will give us 4 bytes of offset. Again, similar to what I explained previously when you add an index in that subscript operator. Okay, now something else that we can do is we can dereference these, and then that is similar to this. So I'll remove that address of operator, and these should now all give us what you would expect, which is the second element in that array, which should print 2. As you can see, those will now print 2. Actually, I'll just change the values in the array slightly, so we'll do 2, 4, and 6 maybe. And then if I just go and build around that again, we'll get 4 printed out each time. Alright, what if I take away those parentheses, build and run, we'll get 3 now instead of 4, and that's because it's going to dereference that first. The pointer, it's actually going to point to this first element now. Pointer is assigned to demo array, so it's going to point to the first element. We're going to dereference before we add 1 to it. Okay, so that's another reason why you want to add those parentheses. So we can take either one of these. So I'll just take the pointer one and paste it over here. And maybe I'll assign 5 to that. So this here is very similar to doing this. So you go to wherever this array starts in memory. You add 4 bytes of offset. So in other words, you move over to the next element in the array, which will be this over here, and then you change it to 5. So all of these will essentially achieve the same thing. I'll just comment these two out, build and run that. Those will print out 5 now. Of course, I'm not going to build and run each time. You can go and test that out for yourself if you want. So these two notations are equivalent. That's really what it boils down to. Okay, just one more demo. I'll go and print out demo array 0, so the first element. Go and delete that. And I'll assign the second element. I'll go and assign 5 to that. And then here I'll do +2. And maybe change that to 7. And then here I'm going to print out the second element. And then here I'm going to print out the third element by switching this here to ptr +2. Build and run that and we get 2, 5, and 7. Okay, so I'm going to demonstrate the next thing here using the pointer. So I'll just create some space here, separate those out. And let's just get rid of that dereferencing for right now. And let's say we want the exact amount of offset, so the exact amount of bytes, because this might be a bit confusing, right? It's not going to add 1 byte, it's going to add an amount of bytes depending on what this pointer is pointing at. In this case an integer, so that will give us 4. So let's say we want to change that to the exact amount of bytes. Well, one thing we can do is we can essentially convert this to a pointer to a char, and then we can add, instead of 1, we do 4 bytes of offset. And let's pull and run and see if that works. Yeah, that actually seemed to work fine. Okay, but just to be sure that you write the correct amount of bytes into that address, what you want to do is you want to convert that back to a pointer to an integer. So it's going to take this to that offset and then it will convert it back. Okay, and this is just to ensure that we write the correct amount of bytes into that memory location. Otherwise, once again, you might lose some data. Alright, I'll build and run that and this should work fine too. This will work fine even with this here, but that's just because we do a small amount. If we did 700 for example, and we cut this out, notice that we don't get the value that we expect, and you may also get some warnings and stuff. So if I put that back, pull and run, and we'll get the results that we expect. Of course, I'm just showing you all of this. I actually explained some of this in previous videos, but I'm not going to assume that you follow with this exactly. So I'd rather explain it again and then, maybe it's a bit more clear for you. So that was that. Of course, this is a big mess. We can see now, okay, we have 4 bytes of offset, but we have to do this, big thing, and it's just a mess. So it's not really worth it for me. I almost never do it in that way. I prefer to do it like this. But when you use it like this, then again, you need to make sure that you remember This 1 is not going to be 1 byte, it's going to depend on what the pointer is pointing to, or the type that it's pointing to. So in this case, an integer. So that means we do 4 bytes of offset. Here we'll do 8 bytes. Again, 4 times 2 is 8. So in this case, we'll do 8 bytes. Assign 7 to that. So it's 0, 4, and 8. So we assign 7 to here, to this third element. So it'll change from 6 to 7. And then here we print it out. Okay, so I hope that makes sense. A quick summary for you on the subscript and the offset notation. So I have this comparison in the table and have a note right at the top that says when reading from or writing two elements in the array, the notations in the following table are equivalent. Alright, so these two will give you the same result. Basically, it's just going to do some temporary offset. So you can either use the subscript notation or the offset notation using either the array name or the pointer name. If you want some permanent offset, then of course you're going to apply that to a pointer. You're not going to apply that to the array name because we cannot change the address that the array name is going to point to. It's constant. Now of course the index that I pass in is just some integer, and it can also be a literal, so 1 or 2 as we've seen. I'm just using a variable here as an example.